Richard Feynman, Nobel Prize-winning physicist, brilliant mind, legendary explainer, once said, "I think I can safely say that nobody understands quantum mechanics." And he meant it. Developing a reasonably deep intuition of quantum mechanics takes years of serious study. But applying quantum computing, understanding what it can actually do and why it matters, that's something we can cover in a couple of minutes. So let's skip the physics. Instead, let's talk about two things a quantum computer can do that will genuinely change your world. Your laptop thinks in bits. Every bit is either a 0 or a 1, on or off, yes or no. Like a light switch, a quantum computer thinks in qubits. And a qubit can be 0, 1, or, and this is where things get weird, both at the same time. This is called superposition. Think of it like a coin. A regular bit is a coin lying flat, heads or tails. A qubit is a coin spinning in the air. It's both heads and tails until it lands. Now here's why that matters. Two qubits can represent all four possible combinations, 0, 0, 1, 10, and 11, simultaneously. 3 qubits, 8 combinations at once. 300 qubits, more combinations than there are atoms in the observable universe. A classical computer checks one path at a time. A quantum computer can explore an almost incomprehensible number of paths at once. Imagine a phone book with 1,000,000 names, completely unsorted. You're looking for one person. Classically, you'd flip through pages one by one. On average, you'd check about 500,000 entries before finding them. That's how every classical computer searches an unsorted list, one item at a time. In 1996, a researcher named Love Grover came up with a quantum algorithm that changes this completely. Instead of checking one entry at a time, it uses superposition to consider all entries simultaneously, then uses a process that makes the right answer get louder while wrong answers get quieter. You home in on the answer without checking everything. For 1,000,000 items, Grover's algorithm needs roughly 1,000 steps instead of 500,000. That's 500 times faster. Scale that to billions of records, medical databases, financial systems, logistics networks, and this becomes transformative. Nearly everything you do online is protected by encryption called RSA. Your banking app, your emails, your messages. RSA has kept the internet secure since 1977. Here's how it works. Take two enormous prime numbers, each hundreds of digits long, and multiply them together. Easy. But reversing that process, starting with the product and figuring out the original two primes, is extraordinarily hard. Classical computers would take longer than the age of the universe to crack a modern RSA key. That's the lock. The security of the entire internet hangs on the fact that multiplication is easy, but factoring is hard. In 1994, mathematician Peter Shor discovered that a quantum computer could factor these enormous numbers in a fraction of the time. What takes a classical computer billions of years would take a sufficiently powerful quantum computer hours, maybe days. RSA's lock doesn't just get picked, it gets dissolved. This is why governments worldwide are taking this seriously. In August 2024, the US National Institute of Standards and Technology, NIST, released the first official post-quantum encryption standards. New locks, ones designed to resist even quantum computers. Quantum computers exist. Google's Sycamore processor in 2019 completed a specific calculation in 200 seconds that Google estimated would take the world's fastest classical supercomputer 10,000 years. But they're still fragile, error-prone, and limited. Running Shor's algorithm on a real RSA key would require a machine far more powerful than anything built today. Experts estimate we're 10 to 20 years away from that. The quantum era isn't here yet, but it's coming. And when it arrives, the computers won't just be faster, they'll be capable of things that are simply impossible today. Feynman was right. Nobody fully understands quantum mechanics, but thanks to it, we're about to unlock a completely different kind of computing. Things explained simply.